Today we will cover both application layer protocols as well as service discovery protocol, that is SDP. All of you might have heard about all these protocols. My intent here to introduce you to those network protocols which are modified to suit the requirement of IoT. And when you get into IoT world, you will hear such acronyms, and you should be familiar with at least a few of them. There are many, but I am trying to introduce you to very basic important protocols that I feel that you should know. Now, we covered about IoT architecture in the last session, which talks about many layers. What we talked about was 5-layer architecture. What I am showing here is only 3 layers. This perception layer or device layer, or we call it as object layer. Then we combined it with the object abstraction layer. They map to this. Then there is a service layer, which also talks about all the network related things. They are part of that. And then we have application layer, which we saw, and then business layer. Now, these two, I am combining it as application layer here with only 3 things shown at a very high level. Now, there are different architectures which are specific to the application for which they have been developed for. SDN, I introduced you to this when we were discussing about 5G, software defined networking, which is nothing but a network architecture which can be configured at the software level. We don't need to go to the device level and set up the commands, routing table, and access list, application, ACLs. It was the way earlier done with all the Cisco's or even any other network devices. But SDN is something which is at a higher level. The IT administrators uses the software and control the devices underneath. And it doesn't matter whether the device is from which vendor. So that is what is called SDN. And the IoT under SDN environment, we have a flexible agile networking programmability for the context-aware IoT systems, where based on where they are, they will be connecting to the devices or servers, gateways nearby, and then understand their functionality based on where they are. Okay, that is called software-defined awareness of the IoT devices. Okay, a device which is in a fire alarm in a auditorium is different from a fire alarm which is at home. So they have to behave differently based on where they are. So that's how the awareness is built in. There are some IoT architecture which is quality of service is very important. See, some places IoT devices where they are connected to unreliable network, like for example, if it is there in fields where they are supposed to find out the soil moisture or the kind of what needs to be put manure, those kind of things are not very QoS is not very strict. Whereas a fire alarm, an IoT device, protecting a huge mall or a building, they need to be very quality aware. So those kind of IoT devices, they fall under the QoS based architecture. Now, service oriented architecture, that is, what happens is the devices coordinate among themselves to provide some services, specific services to the user. So they talk to each other and then they come up with what services to offer to the environment where they are. Mobility, where the devices are like mobile devices, they can move around, and the way we handle them when they move from different place to place, how they need to be taken care of, that it has to be identified across the network. So they have a different architecture with the purpose is different and the requirements are different. Whereas fire alarm is not going to move around. Once it is fixed in a particular place, it is going to be there. Whereas a mobile first architecture is concerned about mobility of the IoT devices. So just understand that IoT architecture, what you choose depends on the application for which you are designing the system for. That's what I'm trying to drive home here. Cloud things architecture, wherein the devices need to be connected to the cloud. Suppose if it is the purpose of IoT device is to collect information about maybe traffic on a highway and then feed it to the cloud, so that down the line the whole country they can manage their traffic, or if they are trying to identify um, a particular vehicle moving around the city or whatever it is. So those kind of applications wherein a large area is required and the huge amount of data is to be processed, which are that IoT devices are cloud connected. They need to be connected to the cloud, and all the data has to be collected and analysis has to be done. So that's a different architecture. Social IoT architecture is nothing but devices which are connected. Again, it is similar to service oriented. It's an emerging paradigm where IoT devices interact and establish relationship where they are with the nearby devices and the gateway. They exchange information and they build some relationship for achieving a common goal, similar to SOA. Okay, I hope this much of high level architect overview is enough. I'm not going to into the details, but you can read up more based on where you land into. So social IoT architectures are smart retailing, smart traffic management in cities, wherein the nearby traffic signals are to be managed and the vehicles have to be provided information so that they can find an alternate route, or the GPS in the system or the application running in the cars can divert the car based on the traffic in the area. So this kind of social IoT architecture where the devices have to work together around with the other devices in the network. Fine. Now, based on the computing, there are different levels of computing happening. I have already mentioned about this fog computing, cloud computing, and edge computing. So edge computing is nothing but collection of the data and then doing a quick processing of the data. Okay, it could remove the noise, or it could reject, drop some data which is not varying. Suppose if you are monitoring a fire alarm and a cloud is there, it is supposed to send information. It has to only provide a I am alive kind of a message once in a while to say that the fire alarm is active, so that the cloud doesn't bother that, okay, this device is active. But it doesn't mean that it has to keep sending every 1 second information that there is no fire, because only when it event happens, a smoke detection or something happens, it has to communicate. So that kind of having intelligence when to send the data, when the event happens, that needs to send the data, not the data which is stale or not even stale, which is not changing. So that kind of intelligence is built into this edge computing devices. Fog computing is something which is closer to the edge devices, so that it can do some local decisions it can take. Even if it is disconnected from the cloud, it can do some minimum data collection, as well as any actions are to be taken locally that can be handled by fog computing, which is a little more powerful than the edge computing devices. And then the cloud computing, anyway, you are all aware that they need to collect information from different sources and then take a collective decision for all the devices. So this is a different level of architecture based on where they are. Okay, fine. Now let us understand why are we supposed to learn about protocols in the IoT architecture. Now we learned about architecture. Now we are bringing protocol to implement those layers. Now, what are different requirements from the IoT devices with respect to communication? Now, this is one typical example where the devices have some intelligence. Sensors are only collecting data, but they also have a communication capability that they can either communicate with the devices here as well as to the cloud. They can directly send it through gateway. And then cloud, and then there are different backend systems which are doing data analysis. Now, communication requirements are, one is between the devices and the sensors. Now, actually, sensors may not talk to each other, but the sensors will talk to the devices there, which is having some intelligence and software running. They need to communicate among themselves. That's one level of communication. And then the devices need to communicate over the internet with the backend systems through the cloud. Okay, this cloud means nothing but internet, and the devices here, it could be cloud-based systems or maybe a server installed for a particular application. So they need to establish a connection between the devices here and to the cloud. and then a communication which is between the systems here, because there may be different functionalities provided by these systems, but they need to be communicating with each other, maybe to take a collective decision for a city or for a no, in a smart city. I can say that if there is an accident in a place, traffic has to be diverted. That may be handled by a traffic management system for a city. Then police need to be informed that if there is a untoward incident, police need to be informed. And then hospital, maybe ambulance need to be sent to the place where the accident happened. So this is hospital management, this is police, and this is the road traffic management. So these devices need to talk to each other, the servers, to arrive at a particular goal of a smart city. I hope you understand that requirements are not only between the sensors to the cloud, it could be between the servers or between the devices to server or among the devices. So the protocols that we see may handle one of them or many of them or some of them. Okay, so let us see. Before I go into that, let me tell you why we need a protocol. They are needed for devices and systems have to communicate and exchange information with each other. They need to have a common understanding. Otherwise, what is sent by one device will not be understood by the other. A simple example is network byte order. So a device here may be following little endian, another node may be following big endian, while storing the information in their own nodes. But when they are communicating, they need to have a common understanding. That's why network byte order has come in. So this is one good example of why we need a protocol and why we need a clear idea on how data is sent over the network. Okay, not only network, anything which is sent across, exchange between two devices. So interacting entities need to agree on how information is exchanged, where to expect something. So that's why header information is already frozen and they are agreed upon. So protocol is a collection of rules and data format. It is a rule that means if you get this, what you are supposed to do. So TCP and UDP. Suppose if you are sending a TCP packet and a UDP packet, what is the different way this has to be processed by not only the end devices, even the devices which are in the middle. So segmentation, reassembly, all those things need to be taken care of in TCP, and then acknowledgement has to be sent, timeout has to happen on the other end. This all is requirement of the TCP protocol, whereas UDP is the best way of transferring it. If a particular device in the middle encounters a UDP packet, and if it has a traffic jam and the queue, the particular queue here has filled, and then it has to decide which packet to drop, naturally they will drop the UDP packet and then they will keep the TCP packet intact to send it across. Why? Because a TCP packet, it is the receiving end is reassembling all the packets to get the final data to the upper layer. Whereas if suppose one particular packet has been dropped by one of the devices in the middle, all the packets have to be resent by the sender and it has to be received by the receiver. So it is a load on the network as well as on both sender and receiver. So any device here may have to take a decision which packet I should drop. So that needs a protocol awareness. So that's why protocol is important, and you should know what is it supposed to do and how to handle some packets. So we are now talking about protocols. So we have a basic architecture. I am not talking about business layer, and we are only bothered about now this. We have already covered lots of protocols we have seen, Wi-Fi and 5G and Bluetooth, all those things, which are basically to collect information from devices and then send it across to the internet. Now, what we are going to see today is application protocol and service discovery protocols. Okay, I hope you understand the overall picture where it actually falls into. It's a highest layer, business layer we are ignoring. It is implemented through a dedicated application at the device end. So always remember, if there is an application protocol, that doesn't mean that it is only implemented in server. Some part of it has to be running on the device also, because it has to have application awareness and for what it is exchanging information from, and then when it is receiving some information back from the server, it should understand. So any application layer here sending a information will be understood by the application layer here. So if you know the TCP/IP, peer-to-peer communication is happening. So they need to have an understanding of what is being exchanged. Only on the particular level can understand what the other layer is talking about. So application layer is implemented by the browser. Now you know that HTTP and then HTTP secure, all those SMTP, mail transfer protocol, file transfer protocol, transfer protocol, they all implemented by the browser, and we exchange information through internet servers. This layer is responsible for data formatting and presentation. In internet we use HTTP, whereas we can't use HTTP in IoT devices because it is very power hungry and heavyweight. Heavyweight in the sense the amount of code that you write to process HTTP protocol itself is huge, and the amount of messages exchanged is also many, and which is not suitable for IoT. So we cannot use HTTP directly. So we go in for different protocols which are suitable for the devices, IoT devices, which are less power, they are run with batteries, and they have less memory and state information. So IoT devices are not going to be up all the time. See, if your laptop is there, it will be, you can expect it to be on. When it is on only, we need to use it anyway. But IoT devices will sleep most of the time and wake up once in a while. So they need to, the protocols need to take care that the end devices are not alive always, in the sense they are not active always. So the protocols need to comprehend that. Okay. Especially like if I mentioned TCP, they time out based on the response not coming from the other end. But IoT devices, they need to be very patient because they cannot expect the IoT devices to react very fast. So these are the protocols which are specifically defined for IoT devices. So I hope you understand why we need such a different protocols for IoT devices. Now, what is AMQP? It's an advanced message queuing protocol. What happens is there is it's called a exchange or a broker. Okay. Normally this is run as a middleware, IoT middleware. Now the devices may have some services they may be offering. So they will publish that I can do this. Maybe I can identify a smoke detection, I can perform, or I can send you information about the images that I am handling. If a camera is fixed in a road, it will publish saying that I can send images, what I am seeing here, maybe video or audio, or it could be images, still messages, still images. So this kind of what the capability of devices are published, and the subscribers could be police control room or a traffic control room or whatever. They will, those places, they will exchange, they will subscribe for such services, and a broker in between will hold those messages coming from there and then deliver it to them. So they will be queued up, and then there will be a FIFO order. It depends on what is the requirement of a particular service. It could be FIFO or it could be LIFO, but it will be managed by somebody in between. That is called a middleware which is sitting there. So it is a publish subscribe pattern, or PubSub in short form. This framework for exchanging messages between publishers and subscribers. So people subscribe for something, and then they subscribe for some services, and services are published by these publishers, and based on who is subscribing for the information, those people will be delivered the messages. Okay, so mostly it is all done in Java or higher level languages. So this is the broker message that relays messages between publisher to the subscriber. The host or a publishes messages or events to the channel that subscribers can then sign up for. So they will publish their capabilities, and then subscribers subscribe for it. Now, how it is done? It's an open standard application layer protocol, message oriented. As I mentioned, middleware is there. This is used for passing messages, business messages or events. It could be, I can make it as an application layer or a business layer. And what happens is actually the messages have the header, and that header has information about not only what is the payload, also what are the single queue. So there is what I'm saying is it will also have information about how it has to be exchanged. Okay, it could be for one to many or one to one. It could be a multicast. Header has information about messages as well as the routing information. So you know that source routing protocol, you might have heard about source routing. Source routing means based on the device here, it will find out what is the path a packet has to take, and then it will also give you the list of IP addresses, router IP addresses, so that one by one it will be routed to. Okay, so the path is already decided by the sender, and then it goes. So similar source routing can be implemented in AMQP. The broker is responsible for reading the header and receive and route and deliver it. Okay, the devices are not handling them. The broker is handling it. So it could be between two nodes. It could be one to one. So at a high level, just to summarize this protocol, it is for exchanging messages. People subscribe for some services, and the devices which are offering will be publishing it, and there is a broker in between which is handling those delivering of data. That's all, messages. Okay, this at a high level what is that particular protocol does. Now MQTT is very popular and you hear it more often on an IoT. Message queue telemetry transport protocol is also similar to what I explained earlier. The sensors, these clients are all, they publish what they do. Okay, and then they get the published information also, because they should know what the other people in the network are offering, so that the devices can exchange information between among themselves. So they do publish and subscribe. So they receive both the information. Okay, in the MQTT. It is normally for tracking different devices over longer distances. It is for statistics gathering. Okay, for in normal where you are using MQTT, like a traffic pattern or a footfall in a particular mall or in a shop. So this kind of a statistics information. It works on TCP. Okay, mainly you can imagine a protocol which is running on TCP cannot be on a devices wherein power is a problem. So you need to decide, if you are choosing a particular protocol, you have to make a analysis of what exactly it is going on. If it is a UDP, then you can put it on a lower power devices, whereas TCP needs a state awareness. They need to be always alive. They cannot sleep very often. That in the sense, then the TCP connection will be lost. So you have to keep those kind of things in the background. And it also exchanges information between different packages, and then middleware connects it. They have a subscriber, publisher, and dealer. Dealer is nothing but a broker. The writer, or the person who is publishing it, generates the information and transmits the facts to the subscribers to the dealer. Okay, these are different names. Okay, I'm just exposing you to different names so that you understand the IoT literature when you come and read through that. So the dealer guarantees safety by means of authorization and publisher. Okay, this also has a safety feature. All the IoT messages have to have a safety feature, and it also has authorization, so that a middleman in attack, a man in the middle attack will be avoided. Okay, so understand what exactly this is meant for. It runs on TCP. It also has a publish subscribe pattern, and it is basically meant for gathering statistics. So this is what you have to take home as a summary. Maybe when I ask in the exam, don't copy this, paste it on your exam paper. Try to explain in your own words what you understand by them. That actually helps you in retaining this. When you are asked in the interview, you don't have these slides to copy paste to the interviewer. So you should have something in your brain so that you can speak it out. So write in the exam as if you are facing an interview. So which will help you to explain if you are asked what is this CoAP or a protocol does. Okay. So before I go into further, let me see whether any questions are there, or you are all alive, or you are like IoT device slept off. Okay. Oh, I am not sharing. Okay. Did I not do? Um, okay. Can you see the full screen now? Sorry, I didn't see that. You could have interfere. Okay. What is the AMQP like RSS? I don't know what is RSS. I know only RSS party. Really simple syndication. Okay. Maybe you can find out and then let me know. I'm sorry, I don't know about that. Okay. Thank you, Tanmay. Okay. Anant, I don't know what is RSS. Oh, not yet? Okay. I am full screen. I am sharing. What do I do? Okay, I'll do one thing. I'll stop sharing and then again I'll stop it. Always that helps. How is it looking now? Why? I don't know. Okay, somebody can come online if you know what I am doing wrong. Uh, okay, full screen. I don't know why. Only today there is a problem. Oh, go ahead. Yeah, yeah. I think Tanmay, you need to maybe do something on your end. It's a problem maybe with your device. Okay, let me go ahead. I hope no problem. Okay, guys. Now I hope so far you are all with me. Understand what exactly I'm trying to give you overview. Okay, now I don't know how to pronounce it in a short form. Maybe CoAP is better safe to say that. But be alert when someone tells you CoAP or something. I don't know. Okay, guys. Now what is CoAP? I hope you have heard about this RESTful or REST. So let me explain what is it. There's a devices. It could be like a simple alarm or a smoke detector, or it could be a sensor with a camera in it. Okay. Now there is a server and we have a proxy at the end, and then finally they get into the internet. Now you see that HTTP communication is only between these. Okay. As I mentioned, HTTP is power hungry and it's over. It's not a it's a heavyweight protocol. So we can afford to have it on proxy, but not on the devices. So that's why you see that these are all CoAP communication, whereas this is HTTP. Okay. Then from the picture, you should be able to understand that it's an Internet Utility Protocol for constrained devices. Okay, the name means constrained application protocol, means constrained in the sense they have a power hungry, they have the power constraint, memory constraint, processing speed constraint, and the network unreliable network, and then they need to go into sleep for more time. So these are all the constraints they live in. So this protocol is designed for such a constrained devices. It is this is designed to enable simple constrained devices to be connected to the network, even though they are on a low bandwidth network. It's a machine to machine communication, and basically it's a HTTP protocol based, but it runs a reduced version of HTTP. Yes, optimized version of HTTP. Okay. Now let me explain a little bit more about it. It uses UDP. Okay, that's very important thing to remember. So lightweight implementation. It uses RESTful architecture. RESTful means REST, I can tell you, representation state transfer architecture. I will tell you what it is. It means transferring, accessing, and manipulating textual data representations in a stateless manner. Okay, so it's a state transfer protocol in a stateless manner, in the sense it doesn't have to, suppose, let me explain you would have studied in networking. TCP is a stateful protocol because it has to know what packets have been received. It has to maintain the assembly or reassembly, segmentation reassembly. It should maintain the state of what are the packets have been received, what is pending from the network, and then it has to send the acknowledgement. That means what is received, what is not received. Based on that, it has to send the acknowledgement. So it should have a state information about the connection between two devices. Whereas UDP is a stateless protocol wherein you don't maintain any state information. So a protocol, a stateless protocol is less power hungry, or no, it doesn't have to maintain so much of information about exchanges, and it's like a fire and forget. It can receive the packet, it can send a response to the packet and forget about it, whether it has been received or not. It doesn't have to do any acknowledgement, or it doesn't have to do a retransmit of information if it is not received on the other end. So it is a very unreliable communication, and it doesn't maintain any state of what it has done so far. So the protocol stack is always like a fresh in mind. It doesn't maintain any information about what has been done so far. Whether if you see the TCP protocol, it has got a different state diagram. It's a huge state diagram it has to maintain, and then based on the state of a communication, it has to respond back based on the timeout or whatever happens, or based on what it receives. So if it is deployed correctly, the protocol, it provides a uniform interoperability between different applications on the internet. So it's a stateless communication protocol. It runs on HTTP, but it's a stateless information, and it's called RESTful because it exchanges information across devices, and it is a textual data. Okay, you know that HTTP has majority. HTTP was initially developed for text transfer, and then it finally became multimedia communication, wherein images and video or all those things are also embedded into the device in the protocol. An important aspect of RESTful request is that each request contains enough state information that server can answer that. So what I mean by the request, that put and get, all that exchange information that happens in HTTP. Now each request has complete information about the state information. So the receiver doesn't have to maintain any state information for responding back to a request. That's basically what I mean by RESTful. If you remember this line, it is enough to understand what is RESTful. This helps enable caching of specific results without any state information. So you can actually devices in the middle or even the end devices can cache information, in the sense they can keep the temporary copy of them, and they don't need to maintain any state information. Okay, they cache the results locally. The server can cache a result remotely also, or even intermediate architectural element can also cache the result. So what I'm saying is, when you cache the result, you are not sent it across because you are caching it for some purpose, because network is down or the device on the other end is sleeping. So the intermediate device or the gateway which is communicating with the IoT device will cache the information that it has received from the cloud for waiting for the IoT device to wake up and then inform back. Okay, so it doesn't expect the IoT device to be always up. So they need to do a caching facility also. But while caching, it doesn't have to worry about what is the state in which this message was received. So that's why the advantage of CoAP, this protocol helps you stateless communication, so that all the devices can support it without much of processing. Okay. Understand the high level idea of these protocols, why they are there. They are client server based model. Similar to HTTP, get, put, delete, post, all that information is, commands are exchanged, messages are exchanged. They are small size and can be conformable or non-conformable. That means you need acknowledgement or you may not need acknowledgement for all the messages. So you can configure it. In the protocol has the both facilities. And one more most important thing is it has got a security built into it over UDP. It is sent over UDP, but still it has a security feature. That means it may do encryption, a simple encryption, 128-bit or whatever. And then there is a security feature. Client has to do a polling of the server periodically to observe changes to the state. Now, I will tell you one interesting observation. See, in HTTP, what happens is server is there, and then our browser, laptop, they do a polling if suppose they need to get some information from the web server, any changes happening or any new YouTube image or something has been posted. So they have to poll the device, and the client device has to poll the server, okay, periodically to get the information, any changes happening on the server side. Whereas this protocol solves the problem by observe flag. Just one information I thought I'll share it with you. If suppose a client says that I am interested in any changes happening to you, okay, for example, suppose a device, a controller here has sent a command saying that switch off for a while, okay, switch off the camera for a while. Now a camera which is in the road is switched off because based on the command coming from the control room. But they don't have to be polling the control room to say whether I am receiving a command to switch on my camera or not. What we will do is this will send a message saying that I want you to tell me when there is some change happening to the particular command. So if server or a control room, somebody is sending a command to the device to switch on the device, then server takes care of recognizing the event and then informing the client without the client asking for it. So you can always imagine these protocols are meant for making the job of the devices easier, whereas the high-end, the cloud devices or the servers can do more job, whereas the devices at the edges need to be protected and they need to save power. So your protocol should support such features. So this protocol supports that kind of a feature wherein the device can register for something event, and then the event, when it happens, it will be delivered to the device without the device asking for it. So this is kind of a resource discovery by the client devices. Okay, it also provides a resource discovery, and then sensor nodes in the network themselves act as a server. Suppose the devices themselves can exchange information among themselves. Okay, for the clients within the device, within the network. So when coordinating application requirements are there, this protocol supports that also. So imagine this protocol is meant for devices which are having not much of power, so they have some special features to support them. I hope you understand that. Now one more, maybe this is the last, I suppose. Data distribution service, very simple. Here there is no intermediate middleware there. The senders and publishers, the publishers as well as the subscriber, they exchange information directly. Okay, there is nothing in between. That's the only difference you should know. And DLRL is nothing but data local reconstruction layer. This is for sharing of distributed data amongst the IoT devices. It is for sharing the data between different devices. That's why it comes under different application. As I mentioned to you, the example of accident happening and different applications like traffic management, police, as well as a hospital. In a smart city application, they need to be having information that some accident has happened in a particular junction. All of them need to be informed. So you can imagine that DDS could perform the job of exchanging that information among them. So try to always connect with a real life application so that you understand why we need such an application running, protocol running on a particular device or a server. Now, what is DDS? It's scalable, real-time, reliable, overall performance and interoperable statistics change by a subscript and subscribe technique. Same pattern, publish, subscribe, or submit, subscribe. It makes use of multicasting. Okay, now one more additional thing which you not seen it in the earlier protocol is the multicasting capability this protocol supports. And in platforms ranging from low footprint to cloud, this protocol runs on, it can be between two devices. So when I say that it is low footprint to cloud means the DDS both end, okay, it can exchange information between them. DDS running here, DDS running on the device, IoT device, and they exchange information as well as with the cloud, okay, DDS running here. It is between them as well as between the devices here. So that's why you need to have a lower footprint of DDS on these devices. Similar to what you see in TensorFlow Lite, TF Lite, and TF. TF Lite runs on end devices, whereas TF runs on cloud. So similar to that, DDS also can run on either edge devices or on the cloud. So same publisher subscriber. That's why I explained that it in the beginning so that you understand the context. Okay, let me read it out. The protocol does not require any networking middleware. That's what I mentioned. So the publishers can release the information on specific topics, like a temperature sensor may release current temperature of a location, and the protocol itself manages to deliver it to the subscriber. Okay, so there is nothing in between middleware running and collecting the information, queuing it up, and then sending it to different devices. That's why multicasting is supported, because it has to be delivered directly to multiple devices if they subscribe for it. Whereas if it has a middleware, then they can take care of the subscription, multicasting facility. Whereas because there is no middleware, the multicasting capability has to be built into the DDS itself. Okay, you can actually relate based on the architecture, you can relate the features of a protocol. So DDS does not require verifying existence or location of the node. Okay, it's very lightweight. Does not need confirmation of message delivery. So it is like a UDP. Okay, so you cannot send a real time. You can send a real time data, okay, on this, but at the same time you have to live with the message delivery is not there. You need to have another mechanism of sending it again, or retransmitting it. Some other way of communicating it has to be done. Okay. Okay. Now all application layer protocols are done. I will just touch upon service discovery protocol just for the completeness sake. IoT devices need to connect and communicate with web cloud-based services for IoT implementation, of course. Now, cloud and web services applications run on host computers which are identified by unique IP addresses. Now, let me explain what is service discovery. It is like a DNS. You know that in DNS, what happens? You have devices, you have a domain name like www.facebook.com. You don't know the IP address of the Facebook server. So DNS, you don't know the address, IP address of a particular web server, web address. Then we send it to the DNS server, which is, that 8.8.8 is a Google DNS, which you will configure normally in our, I think 8 is correct. So what happens is DNS servers having a unique IP addresses, so that any device, if they don't know how to resolve a particular IP address, they send that information to the DNS server, because they know the IP address of the DNS server, and it goes there, and DNS maintains the directory and sends back the IP address of the particular web server, and then the client sends the packet directly to the web server. So it uses that IP address to send the packet out. So that kind of a service discovery is required at the IoT device also, because when IoT devices come up, they don't have a routing table or any information to know where the IP, where the devices are, where they can get the services from, and how to connect to the cloud server, which it is supposed to connect to. So they need some service discovery, so that the IoT devices, when they come up, they can communicate with the service discovery. They can run the SDP protocol and talk to the DNS servers, and then get the information. Okay, so it's similar to what happens in a network. So there are some protocols meant for identifying or getting the IP addresses of IoT host, which are offering some services. Okay. So this protocol identifies servers hosting IP services, IoT services, and their namespaces, and how do they connect. Unicast or multicast can be there over the network. So why do we need multicast? Because when the IoT devices come up, they don't know which DNS server is maybe active at that time. So they do a multicast, okay, or any cast. Any cast may be a nice way of representing it. Any cast means, what is the difference between multicast and any cast? Multicast means if suppose you want to send it to all three of them, that packet will be delivered to all three. Any cast means, suppose it will be delivered to, suppose you have a set of things, and then it will be delivered first to one. If it is successful and then it is responding back, then you don't need to send it further up. Okay, it will not be delivered to others. It will be, if you get a response from one of them, then you don't need to communicate that packet to the others. So always all the protocols are designed such a way that they reduce the traffic on the network. Is a very, very first criteria on protocol is to reduce the traffic, number of packets sent over the network. So Anycast is a optimization on multicast. So I hope you understand the difference between them, knowledge of networking. So it's a DNS, nothing but DNS. Is a multicast DNS, like service discovery. Service discovery means you want to understand the IP address of the server which is providing a particular service for a IoT device. And service discovery means the protocol stack uses standard DNS messages to deliver it. Okay, it's another protocol on top of DNS to identify which service being offered by some server. It is done in two steps. First, you have to identify the IP address. IP address is identified by DNS. And then, let me explain you what it is actually. A device is there, IoT device is there, and there is a service. Servers are there. Service, it provides services. There are different servers providing different services. Now, first to reach this particular server, whether it is providing a particular service or not, first you need to talk to that server, right? You need IP address of that. To understand the IP address or to know the IP address, you need to run the DNS. You get the IP address and then communicate to that particular server, and then it will send back saying that I am supporting this service or not, what you are looking for. So it's a two-level communication. First, identify where the particular server is, and then ask the particular server whether you providing the service or not. UPnP is a universal plug and play. You might have heard about plug and play for the devices that you connect to the laptop. Our USB SD card or a USB drive is a plug and play device where you can connect the device and then laptop identifies it without you doing anything. This is a protocol which is meant for IoT devices joining a network. So anytime the IoT devices can come up and then join the network. So this UPnP supports a newly joining IoT devices get connected to the network and then communicate to the server, and they become part of it. Okay, in a very high level, this is what is the purpose of UPnP protocol, to support IoT devices which is coming up and joining a network. I hope you understand what these various protocols finally achieve. Remember one thing, that IoT communication is machine to machine. We don't need to have a particular human being configuring a IoT device after connecting it. We want the IoT device get connected. When it powers up, automatically get recognized, and then it becomes part of the network. That is how it has to be. So there is no man in the middle to help the device to join a network. Okay, fine. I hope I conveyed what I wanted to.